Hello to everyone from around the world, and welcome to today's webinar, Demystifying the JESD204B High-Speed Data Converter to FPGA Interface, brought to you by Analog Devices. I'm Chris Keach, and I'll be your moderator. We have just a few short announcements before we begin. Before we begin, I want to point out some of the features of Analog Devices Webcast Console. This webcast is designed to be interactive. Please ask questions at any time during the presentation by typing them in the text area and then clicking the Submit button. Our presenter will answer your questions at the end of this webinar, but please enter them whenever they come to mind. We'll try to get to every question, but if we don't do so today, we will email you a personal response. And later in the program, we will ask you to complete a short survey. Please take a moment to fill this out and submit it. Your feedback is very important to us and will provide Analog Devices with valuable information on the subjects covered in this webinar and how we can improve future broadcasts. The survey will open up for you at the beginning of the Q&A session, and additionally, you can launch the feedback form by using the survey button. And now on to the presentation. It's my great pleasure to introduce Jonathan Harris, Product Applications Engineer, High Speed Converter Group at ADI. Jonathan?
Hi, thank you, Chris. I appreciate the introduction. Today we will be examining the 204 high-speed converter to FPGA interface. As Chris mentioned, I'm a Product Applications Engineer at Analog Devices in the high-speed ADC group. And I've been working with the 204 standard quite a bit and would like to convey to you some of the information I've learned. For the sake of time, I will only be covering just a reasonable amount of the material. We won't dive terribly deep into the standard because it can be quite complex and difficult to understand. So we'll just be looking at a good set of data that will provide you with a foundation to understand the basics of the 204 standard. And there will be some links provided as well to give you further information on where to find details on the specifications as well as good design practices for systems that utilize high-speed data transfer. I will first begin with the discussion of the background of the JESD204 standard. We will discuss the standard's development and the differences that exist between the versions of the 204 standard. The current revision is at revision B. Next, we will look at the link structure and lane configurations of the standard. I will discuss the differences between the different versions, but will primarily focus on JESD204A and B revisions. After taking a look at the link and lane configurations, we'll dive into the key signals and layers within the standard. And again, we will mostly focus on the A and B revision of the standard. We are focusing here because these are the most recent iterations and therefore the most relevant. So in the beginning, to take a look at the JESD204 interface, probably one of the first questions that you might ask is, why do we need it? Most converters currently use either CMOS or parallel LVDS interfaces, so why are these not good enough? Well, we are using differential signaling for parallel LVDS, and that should be good, right? Well, as the speed and resolution of converters increase, the CMOS and parallel LVDS schemes basically run out of gas. CMOS is a bit too power hungry for converters as the resolution increases and speeds increase, and it becomes impractical to use. Parallel LVDS is more power efficient, but it has a limitation of speed as well as I/O count as converter resolution increases. So JESD204 offers us a reduction in pin count for both TX and RX side, and the number of I/O required is dramatically reduced. Not only is the number of data lines reduced, but the clock is embedded, which further reduces the amount of pins required. By achieving such reductions, smaller IC packages and board designs can be used, and the system cost is brought down. The standard is also very scalable, so as the speed and resolution of converters increase in the future, the standard can scale to meet those future demands. So what is JESD204? Well, the JESD204 standard defines a multi-gigabit serial data link between converters and a receiver, most commonly an FPGA, but could also be an ASIC. The original standard was called JESD204 and was released in April of 2006. It described one lane and one link between a converter or converters and a receiver. This version of the standard described a single serial lane that would support multiple converters. A common frame clock is used between the converter and the FPGA, and this clock also serves as the sampling clock of the converter. The standard underwent a revision to the A version in April of 2008. This expanded the scope to incorporate multiple links and multiple lanes. So this allowed for multiple aligned serial lanes to support multiple converters, and it was defined to operate at speeds up to 3.125 gigabits per second, just as the 204 version was. And like the original standard, a common frame clock is used between the converter and the FPGA, and again, that is also the sampling clock for the converter. In August of 2011, the 204B revision was released. This update to the standard added device clocks, which must be harmonically related, and also added provisions to ensure deterministic latency in the system. This version again supports multiple serial lanes for multiple converters, but the data rate of the interface has been specified up to 12.5 gigabits per second. Let's now take a look at some of the key aspects of the 204 standards. An 8B10B embedded clock is utilized, which uses DC balanced encoding. This guarantees significant transition frequency for use with the clock and data recovery designs, and this encoding allows both data and control characters to be used. The control characters can be used in specifying link alignment, maintenance, monitoring, etc. And this encoding also allows for the detection of single-bit error events that occur on the link. Serial lane alignment is achieved by using special training patterns with control characters that allow the lanes to be aligned across the link. This allows for trace-to-trace tolerance to be relaxed in comparison to synchronous parallel LVDS designs. Serial lane maintenance is accomplished through superframe structure and by using specific characters to guarantee alignment. The link quality is monitored by the receiver and is done on a lane-by-lane basis. It is important to note that the link is established and dropped by the receiver based on error thresholds within the JESD204 specification. Let's move on to discuss some key signals in 204A and B systems. The frame clock in JESD204A is a clock signal used in the system that is equal to the frame rate of the data that's on the link. The frame clock serves as the master timing reference for JESD204A systems. In JESD204B systems, a device clock is used to derive the frame rate of the data on the link. The frame clock is not used. The sync bar signal is a system synchronous active low signal that goes from the receiver to the transmitter and denotes the state of synchronization. This signal is synchronous to the frame clock in 204A and to the local multi-frame clock in JESD204B. When the signal is low, it implies the receiver and transmitter are synchronizing. Lanes are defined from lane 0 up to lane L-1, and these are differential lanes that exist on the JESD204 link. Due to the high speed of data transfer, these are typically high-speed CML. It is important to remember that the 8B10B code groups are transmitted over the link MSB first and LSB last. New in the 204B standard is the optional sysref signal. This signal is responsible for resetting device clock dividers to ensure deterministic latency. It can be one-shot, gapped periodic, or periodic, and it is distributed to both converters and receivers in the system. When it is used, sysref is the master timing reference in the 204B system. The frame clock in JESD204A is a clock signal used in the system that is equal to the frame rate of the data on the link. Again, it serves as the master timing reference for 204A systems. The sync bar signal is a system synchronous active low signal that goes from the from the receiver to the transmitter and denotes the state of synchronization. This signal is synchronous to the frame clock in 204A. When the signal is low, it implies the receiver and transmitter are synchronizing. The sync bar and frame clock should have similar compliance to ensure proper capture and transmission timing. For example, LVDS, CMOS, or CML could be used so long as both sync bar and frame clock utilize the same signal type. Again, the lanes are defined from lane 0 to lane L-1, and these are the differential lanes that exist on the link. These operate with the typically high-speed CML drivers, And again, it's important to remember that the data comes across these lanes, MSB first, LSB last. The device clock in JESD204B is a clock signal that each transmitter and receiver derives from the master clock generator circuit. The device clock may have a different period than the frame or multi-frame period. If it differs, then the device transmitter or receiver is responsible for generating the frame or multi-frame clock from the device clock. The sync bar signal is much the same as in 204A, but in this case it is synchronous to the local multi-frame clock. Again, new in the 204B standard is the optional sysref signal. This is responsible for resetting the device clock dividers to ensure deterministic latency in the system. And as I mentioned, it can be one-shot, gapped periodic, or periodic, and it is distributed to both the converters and the receivers in the system. When used, it is the master timing reference. And just as in 204A, the lanes are defined from lane 0 to L-1, and they use high-speed CML. The JESD204 standard is a layered specification. So here we'll take a look at the different layers that exist within the specification. The transport layer maps the conversion samples to and from non-scrambled octets. The scrambling layers can optionally take those octets and scramble or descramble them in order to reduce EMI effects by spreading the spectral peaks. Scrambling would be done in the transmitter, descrambling obviously done in the receiver. The data link layer is where the optionally scrambled octets are encoded or decoded to or from 10-bit characters. This layer is also where control character generation or detection is done for lane alignment, monitoring, and maintenance. The physical layer is the serializer, deserializer, or SERDES layer responsible for transmitting or receiving the characters at line rate speeds. This would include drivers, receivers, and clock and data recovery circuits. This is just a simplified visual representation of the layers of the 204 specification. This will allow you to see the data flow through the transmitter and receiver along with the timing reference signals used in the system. You can see the flow goes from the TX application layer through the transport layer, becomes optionally scrambled, through to the data link layer, and then onto the transmitter physical layer, through the receiver physical layer via the high-speed serial lanes. Then it proceeds through the data link layer of the receiver, onto the transport layer. It is optionally descrambled, and then finally ends at the receiver application layer. Let's now dive into the transport layer of JESD204 standard. A single converter can be mapped to a single lane link or can be mapped to a multi-lane link. The same holds true for multiple converters in the same device. The converters can be mapped to a single lane link or into a multi-lane link. And the conversion samples are recommended to be mapped into 204 words on 4-bit nibble boundaries. The figure at the right here shows the mapping of converter samples into the serial lanes. It is parameterized such that it covers all of the aforementioned cases. So for the sake of time, I would encourage you to download the presentation when it's made available and study this chart to further understand the mapping of these samples. The optional scrambling layer resides between the transport layer and the link layer. It is implemented in order to reduce spectral peak emissions on the high-speed serial lanes between the transmitter and receiver. The block utilizes a self-synchronous scrambling pattern that has the polynomial 1 plus x to the 14th plus x to the 15th. The data is scrambled prior to the 8B10B encoder and is descrambled in the receiver after decoding. Since the scrambling pattern is self-synchronous, the two shift registers at the input and output must not be set to the same initial setting. Otherwise, the scrambling function would not work. The descrambler is implemented in such a way that it will always catch up and self-synchronize to the scrambler after 2 octets of data. This layer should have the ability to be bypassed since not all systems may require the data stream to be scrambled. So there are 3 distinct phases of link establishment. So the first phase in establishing the 204 link is what's called the code group synchronization. And in this phase, each receiver must locate K28.5 characters in its input data stream utilizing clock and data recovery techniques. And once a certain number of these characters have been detected on all the link lanes, the receiver block will then deassert the sync bar signal to the transmitter block. In 204A, the transmit block captures the sync bar, and after a fixed number of frame clocks, it starts the initial lane alignment sequence. In 204B, the transmit block would capture the change in sync bar and start the initial lane alignment sequence on the next local multi-frame clock boundary. In the second phase, the initial lane alignment sequence, or ILAS, the main purpose of this phase is to align all the lanes of the link and verify the parameters of the link. During this phase, the link parameters are sent to the receiver to designate how the data will be sent to the receiver block. The ILAS consists of 4 or more multiframes, and the last character of each multiframe is a multiframe alignment character called a control character. The first, third, and fourth multiframes begin with an R control character and end with an A control character. The data in between them is ramp data. The receiver uses the final A control character of each lane to align the ends of the multiframes within the receiver. The second multiframe will then contain R and Q control characters followed by link parameters. To continue on with the ILAS, the additional multiframes can be added to the ILAS if needed by the receiver. After the last A control character of the last ILAS multiframe, user data starts. In systems where no interlane skew management is needed, the ILAS can be bypassed, given that both the transmitter and the receiver support this mode of operation. Then the user data begins. In this phase, user data is streamed from the transmitter block to the receiver block. Data can be optionally scrambled, yet scrambling does not start until the very first octet following the ILAS. The receiver block processes and monitors the data it receives for errors, including incorrect running disparity, not in table, both 8B, 10B errors, unexpected control characters, an incorrect ILAS, an interlane skew error, and that's monitored through a practice called character replacement. If any of these errors exist, it is reported back to the transmitter in one of a few ways. Sync bar can be asserted, which would cause resynchronization by sync bar being pulled low. Sync bar reporting, the sync bar could be pulsed for a frame clock period if an error occurs, and reporting may also be done via interrupt if so equipped, but interrupt is not covered by the 204 specification. So this diagram provides a visual representation of the link establishment procedure. The procedure begins again with the code group synchronization phase. Then the receiver would deassert the sync bar signal, initiating the initial lane alignment sequence, or ILAS. And once the lane alignment sequence is completed, the user data is then valid. And again, for the sake of time, I would encourage you to download the presentation and keep this diagram handy. It is quite helpful in understanding the link establishment. So during the initial lane alignment sequence, the data link layers are responsible for aligning the lanes in the receiver. The placement of A control characters are used to align the lanes in the receiver. The JESD204A and B specifications require that the A control characters be separated by at least 17 octets. This mitigates the effect of a large amount of system skew. And in 204A and B systems, skew is defined in 3 possible scenarios. The first, with one transmitter block and one receiver block. Second, with multiple transmitter blocks and one receiver block. And the third, with one transmitter block and multiple receiver blocks. Upon reaching the user data phase, character replacement and the link layer allows for frame and lane alignment to be monitored and corrected if necessary. Character replacement is performed on both frame and multi-frame boundaries with different implementations between the transmitter and receiver. First, let's take a look at transmitter character replacement. There are 2 cases, one for the frame-based and the other for multi-frame based. In frame-based, if the last character of a frame is identical to the last character of the previous frame on a given lane, then the transmitter will substitute that character with an F control character. This is done also if the last character of the previous frame is a hex value FC when scrambling is enabled. In multi-frame-based character replacement, if the last character of a multi-frame is identical to the last character of the previous multi-frame on a given lane, then the transmitter will substitute the character with an A control character. In this case, character replacement is also done if the last character of the previous multi-frame is a hex value 7C when the scrambling is enabled. In receiver character replacement, the receiver must do the exact opposite of what is done in the transmitter. If it detects an F control character, it is replaced with the final character of the previous frame. When an A control character is detected, it is replaced with the final character of the previous multi-frame. And when scrambling is enabled, the F control characters get replaced by hex value FC, and the A control characters get replaced by hex value 7C. If the receiver detects F or A control characters in the wrong place, it can realign the lanes. However, during this operation, data will be corrupted. Let's take a closer look now at the implications of character replacement. The F and A control characters may not come along very often, so it is possible that the data could be bad for a while before the receiver recognizes that it is bad. This means potentially that garbage data could be sent for some period of time. However, if the error is in the clock and data recovery or the high-speed link, the 8B10B error detector should see this well in advance. If realignment is supported, each lane can realign to either an F or A control character. The JESD204 specification does include information about realigning characters or alignment counters on the fly. Unless the transmitter or receiver skips a character clock, there should not be a problem. So where would this make sense? Well, in a sparse data system or packet system, this is beneficial so that data would not be lost. Also, for systems with dense data transfer, realignment will be preceded by a stream of garbage data. The JESD204 standard requires that at least 4 different types of errors be detected in addition to the alignment errors. Incorrect running disparity on the link is monitored by both the transmitter and the receiver. Not in table errors are also monitored, and when a character not in the 8B10B code table of characters is transmitted, an error is generated. Control characters that are out of place also flag an error. Last code group sync errors are flagged. These would include errors such as wrong links, wrong structure, or mismatched link parameters. A system designer may choose to support more error detection, but these 4 types of errors are required as a minimum by the standard. Moving on to the JESD204 physical layer, this is where characters are transmitted and received at line rate speeds. The physical layer includes serializer, deserializer, or SERDES blocks, drivers, receivers, clock data recovery, etc. These blocks are often designed using custom cells since the data transfer rates are very high. In the JESD204 and 204A standards, both support speeds up to 3.125 gigabits per second. The 204B revision of the specification supports 3 possible speed grades. Speed grade 1 supports up to 3.125 gigabits and is based on the Optical Internetworking Forum specification SXI5-0.10. Speed grade 2 supports up to 6.375 gigabits and is based on the CEI-6G-SR specification. And speed grade 3 supports up to 12.5 gigabits per second and is based on the CEI-11G-SR specifications. We'll take a closer look at these 3 specifications in the next few slides. Here we have a table that gives the line rate, differential voltage, and rise-fall time and total jitter for the signals in the physical layer of the JESD204 standard. The higher speeds have reduced required signal amplitudes to make it easier to maintain high slew rate. These high-speed signals with fast rise and falling edges place tight constraints on board level design, so it's imperative to pay careful attention to trace impedance, links, layer stack up, etc. to ensure good system operation. One must have a good set of physical design rules to work from in order to have a properly working system. I had mentioned deterministic latency a few times, so let's take a closer look to understand this a little better. Latency is defined as deterministic when the time from the input of the JESD204 transmitter to the output of the JESD204 receiver is consistently the same number of clock cycles. When you have a parallel implementation, deterministic latency is simple, since clocks are carried with the data. However, in a serial implementation, multiple clock domains can exist, which can cause non-determinism. The JESD204 and 204A specifications do not contain any provisions for guaranteeing deterministic latency. In the B version of the specification, there are three subclasses of devices described. These three subclasses are 1. No support for deterministic latency, 2. Deterministic latency using sync bar, which is good with converters that operate up to 500 megasamples, and 3. Deterministic latency utilizing sysref, which is used with converters that operate at sample rates above 500 megasamples per second. For converters operating at speeds of less than 500 megasamples per second, the sync bar signal can be used to guarantee deterministic latency. Once the link synchronization has occurred, the receiver will deassert sync bar. The transmitter will capture this event with the frame clock. The latency in the transmitter from the point that it captures the sync bar until the beginning of the ILAS must be constant. And with the latency known, as well as the receiver knowing when it deasserted sync bar, the latency of the forward path is known and can be corrected. It is important to note that sync bar signaling is a system synchronous, and it must meet setup and hold times relative to the frame sample edge at the transmitter. If not, there can be issues with the link. Sysref is used for converters with sample rates above 500 megasamples per second. Unlike sync bar, sysref is a source synchronous signal, meaning the timing of the system depends on the interaction of two devices. The sysref signal is intended to future-proof the specification in order to account for higher sample rate converters, as well as provide the best possible accuracy with the least amount of complexity. In JESD204B, the sysref signal is used to align the internal dividers from the device clocks and to act as the master system reference, which aligns all local multi-frame clocks. This is what is used to ensure the deterministic latency. The signal can be low-speed periodic, gapped periodic, or can be one-shot. In the receiver, sync bar is asserted from the local multi-frame clock edge instead of the frame clock edge. Likewise, in the transmitter, the ILAS is launched from the local multi-frame clock edge instead of the frame clock edge. This makes the sync bar signal effectively asynchronous to the frame clock and system synchronous to the local multi-frame clock. When using sysref, the system is effectively 100% source synchronous. Now let's take a look at the link parameters and control characters of the JESD204 standard. L signifies the number of lanes per converter device. M is the number of converters per converter device. S is the number of transmitted samples per converter per frame. N prime is the number of transmitted bits per sample, which is the JESD204 word size. N is the number of conversion bits per converter. F is the number of octets per frame. And HD signifies if high-density user data format is being used. In terms of the control characters, K control characters are used for code group synchronization. F control characters are used for frame alignment. A control characters are used for multi-frame alignment. R control characters are used to begin a multi-frame. And Q control characters begin lane parameter data and initial lane alignment sequence. Some terminology to keep handy when working with the 204 standard includes the following. An octet is a group of 8 bits serving as input to the 8B10B encoder and output from the decoder. A nibble is a set of 4 bits, which is the base working unit of the JESD204 specification. A character is a 10-bit symbol generated by the 8B10B encoding scheme. The character clock is a clock running at the character rate used to process the characters of a system. A code group is a set of 10 bits in the serial data stream that are used to convey octets. The running disparity is the measure of current DC imbalance on the link used to code and decode 8B10B code groups. The frame is a set of consecutive octets in which the position of each octet can be identified by reference to a frame alignment signal. The frame clock is a system clock which runs at the frame rate. In 204A systems, the frame clock is the absolute timing reference in the system. A multi-frame is a set of consecutive frames in which the positions of the frames can be identified relative to the multi-frame alignment character. Multi-frame clock or local multi-frame clock is a clock in the system which runs at the multi-frame rate and determines the location of multi-frame characters which are used for lane alignment. Typically, the clock is a divided version of the frame clock, which is local to the transmitter or the receiver. In the 204B specification, this clock will be the absolute timing reference. A lane is a differential pair between the transmitter and the receiver. The data link or link is a set of data lanes which provide a conduit for the data to be transferred from the transmitter to the receiver. A multipoint link is a data communication link with 3 or more devices. These 3 devices may be 2 transmitters and 1 receiver, or may be 2 receivers and 1 transmitter. A transmitter is a single lane's worth of encoding, serialization, and driving. A transmitter block includes all the transmitters for a link. The receiver is a single lane's worth of capture, deserialization, and decoder. Receiver block are all the receivers for a link. And then a converter, of course, would be a single converter in a package, and a converter device would signify a package with 1 or more converters. Now that we understand a little bit more about the link parameters, let's take a look at setting up a JESD204 link. First, let's determine the number of converters in the device, signified by the letter M. Next, what is the sample resolution of the device, which would be N? Well, a 12-bit converter would set N equal to 12. Then we would need to set the word size, N prime. The converter sample resolution is broken into nibbles. 12-bit converters have 3 nibbles, while 14 and 16-bit converters would have 4 nibbles. We multiply the number of nibbles by 4 to obtain the value of N prime. It can be advantageous to have N prime equal to 16 so that 8 to 16-bit converters can be handled with the same transmitter or receiver. A non-complete nibble is padded with either control bits, CS, or tail bits, T, and must satisfy the equation N prime equals N plus CS plus T. For example, a 12-bit converter with a 16-bit JESD204 word size leaves 4 bits for either control bits or tail bits. Next, we need to ask how many samples will easily fit into a frame, which would be S. This is determined by the frame rate and the transmitter-receiver internal characteristics. In low-speed simple converters, S is often set to 1. For high-speed complex converters, the value of S should be based on 2 things. The JESD204 data rate, which equals M times the sample rate over a decimation or interpolation factor, and 2, the desired frame clock rate. The value of S is then determined by dividing the 204 data rate by the frame rate. Let's look at some examples. Let's consider a simple ADC with no decimation and with a sample rate equal to 156.25 megahertz. The desired frame clock rate is, of course, 156.25 megahertz, which means S is equal to 1. Now consider 2 ADCs with decimation equal to 2 and a sample rate of 625. The desired frame clock rate in this case, again, we would like to have 156.25 megahertz, which would mean S would be equal to 2 times the sample rate, divide by 2, divide by 156.25, which would equal 4. Now we must ask how many lanes are needed, which would be L. This is determined by the maximum required line rate per lane. The line rate per lane can be calculated by the following equation, where Fs is equal to the sample rate per S samples. Lane line rate would equal M times S times N prime times 10 over 8 multiplied by the sample rate, all quantity divided by L. Let's again take a look at some examples. Let's consider a 14-bit ADC with 1 sample at 312.5 megahertz. So in this case we have M equal to 1, S equals to 1, N prime is 16, and FS is 312.5 megahertz. With L equal to 1, the lane line rate would equal 6250 megabits per second. With L equal to 2, the lane line rate would equal 3125 megabits per second. Consider now two 12-bit ADCs with two samples each, as in an IQ system, with sample rate equal to 625 megahertz. Here we have M equal to 2, S equal to 2, and FS equal to 625 megahertz. With N equal to 12 and L equal to 4, the lane line rate would equal 9.375 gigabits per second. With N equal to 16 and L equal to 4, the lane line rate would equal 12.5 gigabits per second. And with N equal to 12 and L equal to 8, we calculate a lane line rate of 4687.5 megabits per second. And last, with an N equal to 16 and L equal to 8, the lane line rate would be 6.25 gigabits per second. Next, let's look at how many octets are transmitted per frame F. This is calculated from the equation F equals quantity M times S times N prime divided by quantity 8 times L. So for example, a single 14-bit ADC with one sample on one lane, where we would have M equal 1, S equal to 1, N prime equals 16, and FS equals 312.5 megahertz. F would then be equal to 2. Last, we ask if high density mode is being used. If so, then HD equals 1. When in low density mode, partial conversion words at the end of a group of F octets are avoided by adding tail bits. If high density mode is being used, then conversion words may break at the frame boundary. Once we have all the link parameters set, we need to take a look at the frequency relationships that need to be determined. First, the line rate was calculated. And remember that the line rate was M times S times N prime times 10 over 8 times Fs divided all quantity by L. The character clock is then the line rate divided by 10. From earlier, we calculated the frame clock from the word size N prime and the number of samples per frame S. To then derive the multi-frame clock, we divide the frame clock by K, where K is an integer number of frames, and it must be chosen so that the number of octets in a multi-frame not fall below 17. We have discussed in a good bit of detail general methods for maintaining good signal quality. Let's now take a look at how signal quality is measured. In serial differential interfaces, the eye diagram is a common measurement of the integrity of the signal. Shown here is the transmitter eye diagram for a JESD204 operating at speeds up to 3.125 gigabits per second. The table at the top of the slide gives the details on the timing, the voltage levels, impedances, and the return loss. The table to the bottom left gives timing as it relates to the figure on the bottom right. The figure at the bottom right is commonly referred to as an eye mask. The signal must not encroach onto the beige area of the figure, but must stay in the white area at all times. And the table defines the conditions for which the transmitter must meet the eye mask. There is also a similar version for the receiver. I would encourage you to download the slides when they are made available to study this, and also would encourage you to take a look at the specifications for the higher data rates available in the 204B standard. Here, the receiver eye mask and specifications are shown. Again, we are showing for speeds up to 3.125 gigabits per second. It's very similar to what was shown on the previous slide for the transmitter. The main difference you will note here is that the eye mask has relaxed limits for the transition areas and for the maximum and minimum voltage levels. This is due to the signal getting slowed down and attenuated as it crosses the physical media, i.e. the board, connectors, transmission lines, that all exist between the transmitter and the receiver. So, to summarize, the JESD204 standard has evolved and continues to evolve to meet current and new converter interface requirements. As it continues to evolve, improvements are being made to make a more scalable and robust standard. The JESD204 standard was introduced and is being used because of the increased resolution and speed of the converters available today. As the resolution and speed increase, the standard continues to scale and push data rates from the original 3.125 gigabits per second all the way up to 12.5 gigabits per second now, and possibly higher in the future. As these speeds increase, physical design is of utmost importance. The use of good design practices for transmission lines is important. Properly terminating the system becomes key. One must know and understand return current paths in a design, and it is imperative to be able to measure and understand measurements of signal integrity so that a properly working JESD204 system can be designed and implemented. I appreciate your time and would like to now turn things back over to Chris. Thank you again for attending the webinar. I hope you have enjoyed learning a bit more about JESD204. Thank you.
Thank you, Jonathan, for that terrific talk. Before we answer some of the questions that were submitted during this webcast, I want to remind you that the survey is now open for your responses. We really want to hear from you so we can continue to make our webcasts as helpful to your design challenges as possible. We'll now move on to the question and answer section of the presentation. If you have a question for our presenter, please submit it now by typing in the text area on the left-hand side of your screen and then click the Submit button. And with that, we'll start the Q&A with questions already received during this webcast. Our first question for Jonathan. Jonathan, the JESD204B provides provisions for deterministic latency. Why is it important to have deterministic latency?
Oh, thanks, Chris. That's an excellent question. Deterministic latency is important in many applications. These would include complex IF for communications apps, multiple converters in a mil-aero application such in radar, where multiple converters need to have a known timing relationship. And then in DAC applications, a number of these require that all the DACs and two or more chips have the same data in the DAC output latency within one DAC sampling clock cycle. And if the same signal is input to all DACs, the same signal needs to be output by each DAC on the same FDAC clock cycle. Such applications here would again be communications applications like wireless macro base stations, again military radar, and then I&I waveform generators.
All right, Jonathan. So our next question for you, the JESD204B specifies different speed grades. Why is there a need for these different speed grades?
Another great question. This was done to accommodate not only various converter resolutions and speed, but also the migration and process technologies to faster speeds. So as converter technologies are evolving, process geometries are getting smaller, and so current technology is just beginning to push the envelope of these higher speeds. So the speed grades are a way to allow the technology to catch up and be able to accommodate the faster data rates, and also help future-proof the specification and allow it to be scalable to meet increased converter resolutions and speeds.
All right, Jonathan, and it looks like we have time to sneak one more question in. As the data rate increases in the JESD204B, the peak-to-peak voltage levels also decrease. What's the reason for this?
This is done to ease the requirements in the physical interface of the transmitter and the receiver. So as the data rates go higher, it becomes more difficult to meet edge rates, i.e. slew rate. So the amplitude is reduced to ease constraints on the physical interface in the transmitter and the receiver.
All right, well, thank you, Jonathan. That looks like about all the time we have for questions for today. If we didn't get to your question, then someone will get back to you via email. Thank you once again to Jonathan, and finally a big thank you to all of you who attended today's webcast. Please join us on May 16th at 12 p.m. for solving isolation challenges in power supply applications. We hope to see you for this and other future webcasts presented by Analog Devices. This webinar is copyright 2012 by EE Times. The presentation materials are owned by or copyright by Analog Devices, which is solely responsible for their content. The individual speaker is solely responsible for his content and opinions. On behalf of our speaker, Jonathan Harris, I'm Chris Keach. We'd like to thank you for joining us, and we hope you have a great day.